All right, here we go, I think. Yes. Sorry, fighting with new technology here. Okay, so today we are going to learn about variable forces, all right? And so probably the most common example of this is drag force or air resistance, as we called it in the past. But before we can get there, we got to do a little bit of calculus, all right? So a lot of you will have learned this, but I know I always have, a couple students who are in pre-calc, and this might be new for them. And I think this will just sort of like highlight the couple simple, I say simple, the couple calculus skills that you're going to need to do this unit. Okay, so here we go. So let's talk derivatives for a minute, all right? So here I've just got a bunch of derivatives, and so what we're going to do is just use the power rule to evaluate all of these, all right? So we know that the derivative of x cubed with respect to x, so remember, you just, you decrease, well, you bring your exponent down up front, and then you decrease the exponent by 1, right? Okay, so for this next one, bring the 2 up front, decrease the power by 1, so you just get 2x, right? On this next one, here it's x, so that's just x to the first power, right? So bring the exponent up front, times x to the, let's see, decrease 1 by 1 gives you 0, x to the 0 is 1, so you just get 1, okay? Here, the derivative of a constant, for this next one, the derivative with respect to x of 1 is just 0, right? Okay. Now, let's see. Now, what about this next one? So let's see. So for the next one, the derivative with respect to x of 1 over x, that's the same as the derivative with respect to x of x to the negative 1, right? So once again, I can bring my exponent down up front, times x to the, and then I decrease my power by 1, so I get x to the negative 2, right? Okay. And then if I do the next one, if we do this one, we're going to do the same thing. So this is the derivative with respect to x of x to the negative 2. So bring the negative 2 up front, and then you get x to the negative 3. All right, and then so for the last one, we're going to get the derivative, oops, I wanted that to be green, I'm trying to alternate my colors, of x to the negative 3, and so that's going to give you negative 3 x to the negative 4th, right? Okay, so you've seen this before, right? All right, so a thing that I guess I want to point out before we go any further on this is the following. So look, when I took my derivatives, look what happened. One of my answers gave me x squared. One of my answers gave me x to the first. This one gave me x to the 0. This one cannot be expressed as x to any power, right? There's no way you can raise x to some power and get 0. So that one doesn't work. And then we've got x to the negative 2, x to the negative 3, x to the negative 1. But we didn't get x to the negative 1. None of our derivatives gave us x to the negative 1. Okay? So I wonder if there's a thing that we can take the derivative of and get x to the negative 1. And it turns out that there is, which is the thing that is going to be new to you. So it turns out that if you take the derivative with respect to x of the natural log of x, that gives you 1 over x. Okay? So if you don't remember, natural log is a logarithm. So the natural log of x is the same as log base e of x, all right? And then just remember, e is, it's another like magical math number, kind of like pi, right? Like pi is 3.14. E is this other magic number. It's like 2.71 or something like that, okay? All right, so let's do one that's a little bit more complicated here. So what if I gave you this? What if I asked you to find the derivative with respect to x of the natural log of, I don't know, whatever, 2x minus 8, say, okay? Well, so here we got to use the chain rule, right? So I'm going to take the derivative of this thing, and it's going to give me 1 over 2x minus 8, but then I have to multiply that by the derivative of the thing inside the parentheses, right? Okay, and the derivative of that is 2, right? So you get 1 over 2x minus 8 times 2, which you could just write as 2 over 2x minus 8, and then you could simplify it, right? Okay, so that is a thing that you need to know, okay? Now, we will be using this actually going the other way. We're going to be using it to be taking integrals, all right? And the two really common ones that we're going to be using are these. We're going to need to know, well, here, it's these two. We need to be able to take the integral of those two things, okay? So, here's what we need to know. We'll do this in red, how about? So, the integral of x to the negative 2 with respect to x is, well, let's see. Well, so, and I guess maybe I should also say this is the same as the integral of 1 over x squared dx, right? Same thing. Okay. So, so the question is, what thing do I take the derivative of to get this? Well, it's x to the negative 1, right? Because now if I take the derivative of that, when I subtract 1 from negative 1, it gives me negative 2. But I would bring this negative 1 down up front, so I need a negative 1 here to get rid of that, right? So take a minute and convince yourself that if you take the derivative of this, that it gives you that, okay? All right, so that is one of the two things that you need to know, okay? And then secondly, the integral of 1 over x dx. So your logic would be, well, let's see, I know that that is the same as the integral of x to the negative 1 dx, right? And so then you would think, okay, well, this is, I can just use my power rule, right? But so then the problem is, you know, when you take your integral, your power has to go up by 1. So if you go up by 1, you get x to the 0, right? Which would just give you a constant. So that doesn't make sense, right? Okay, if you try to use the power rule, it sort of doesn't work. Oops, sorry, I was trying to do frowny face. All right, so that doesn't work, right? So when that happens, you go, oh, this is the weird one, right? This is the one where the power rule doesn't work, and so I have to use the natural log, okay? So this becomes, none of this works, so I'm going to do the integral of 1 over x dx and go, oh, that's the natural log of x, okay? So those are the two sort of new calculus-y skills that you need. All right, so let's apply that to some maybe trickier ones, right? Okay, so let's do this one. In fact, this would be a great time for you to pause the video and see if you can solve these on your own. Okay, I will assume that you've done that, and we'll do this. All right, so for this first one, this is the same as the integral of 5x to the negative 2 dx. So let's try the power rule. So let's see. So when I take my integral, my power has to go up by 1. So that's going to give me x to the negative 1. So then when I take the derivative of this, negative 1 times what is 5? So this has to be negative 5, right? Okay, so that's that first one. For the second one, let's see. This is the same as 5x to the negative 1 dx. So when I use my power rule, let's see, my exponent's going to go up by 1. That's going to give me x to the 0. Oh, that doesn't make sense, right? Oh, so I'm going to use a logarithm. So I'm going to write this then. I'm going to go, oh, well, that's the same. Let's see. So this is the same as 5 times the integral of 1 over x dx, right? Because you can pull out the 5. Oh, and the integral of 1 over x is, we decided, natural log of x. So this is 5 times the natural log of x. All right, and then for this last one down here, so it's kind of the same idea, right? But the problem is that this thing is a little bit more complicated, right? So your math teacher would probably teach you to do this by using substitution, where you'd go, oh, well, let's let u equals 2x minus 8, and then let du equal, well, the derivative of this, so that would be 2 dx, right? So, well, let's do that then. So let's see. So if I do that, I'm guessing you guys have all seen this before somewhere, right? So this becomes, let's see, this is 5 times the integral of 1 over u du, sort of, but du would be 2 dx, so I got to divide by 2 to get that to work out, right? And so that gives me, sorry, I haven't done integration by substitution in a long time. I probably should have written this out first. 5 halves of the natural log of u, which is 5 halves the natural log of 2x minus 8. All right, so there you go. All right, so if that didn't make sense doing it by parts, here's how I probably would have done this without. I probably would have said, all right, well, let's see. The integral of 5 over 2x minus 8 dx. Well, I can see that this is on the bottom, so that and it doesn't have an exponent, right? So this is kind of like 1 over x, but the x is more complicated, right? So this becomes the same as 5 times the integral of 1 over 2x minus 8 dx. And then I know that this is going to give me a natural log. So this is 5 times the natural log of 2x minus 8, right? So that's the thing that I want to take the derivative of to get me that, right? But when I take the derivative, I'm going to have to do the chain rule and take the derivative of this also. So if I take the derivative of this, I'm actually going to get 10, right? Because you got to multiply by 2. So you got to divide by 2 to undo that. Okay, so I probably would have just done it by logicking through it. All right, so there you go. Now, if I lost you there, find time to come talk to me. All right, and we can do some practice problems on it. All right. Okay, so great. So why do we need all this? Before we go to why we need all this, one other quick thing. So logs, let's talk about logs here for a minute, all right? So first of all, if you don't remember what a natural logarithm is, oh, come on, you stupid computer. So remember, this statement here, the natural log of x equals y, is the exact same thing as saying that e to the y power equals x, okay? So I don't know if this helps, but I always think of it like this. In the same way that squaring something and square rooting it are their inverse functions, right? Squaring something undoes a square root and vice versa. Similarly, natural log and e to the are inverse functions of one another, okay? So if you wanted to get, create this relationship here algebraically, all we're doing is we're taking both sides of this equation and we're going to raise them both to the e power. So this is e to the power of natural log of x, and this is e to the y power, okay? And it turns out that the e to the and the natural log cancel each other out and just leave you with x. So you've got x equals e to the y, okay? So that is definitely a thing that you're going to need to be able to do, okay? Convert between natural log equals and e to the, okay? All right. So please make sure you know that. All right, so moving on. Let's see, natural log of a times b. It turns out there's a mathematical fact that tells us that the natural log of a times b is the same as the natural log of a plus the natural log of b, okay? And similarly, division just becomes subtraction. So this next one, natural log of a divided by b, is the same as the natural log of a minus the natural log of b, all right? And then finally, down here at the bottom, the natural log of a to the p power, well, that's the natural log of a times a times a times a times a, right? Which becomes the natural log of a plus the natural log of a plus the natural log of a. So you get p copies of the natural log of a, okay? I always just remember that you bring the power down up to the front, okay? All right, so those are some tricks that you might need to use. Definitely, just off the top of my head, I can think of examples that I've done in the past that use these. So make sure you know those, and then this one is, helpful. All right, great. So last year in honors, we learned about air resistance, okay? And so the idea is air resistance is this force that resists the motion of an object moving through the air, all right? The more generic term for it is drag force, okay? Because it doesn't necessarily have to be air, right? Like you could have a thing moving through water, and then you have water resistance, right? So drag force is sort of the resistive force as an object moves through a fluid, whether it's a liquid or a gas or whatever. As your object moves through that fluid, the fluid is going to push back on it, and it creates this thing that is called drag force, okay? And it turns out that that drag force depends on these things. It depends on the shape of the object, the density of the fluid that the object is moving through, right? Which is why it's harder to walk through water than it is to walk through air, okay? And it depends on the speed of the object, okay? So in English, the faster your object is going, as your velocity increases, so does your drag force. That also increases, right? Okay, and then we talked about terminal velocity last year. Usually we were talking about an object that was falling, right? So here's your force of gravity pulling it down. And the idea is as it goes faster, your drag force gets bigger and bigger and bigger. And eventually there becomes a point where these two guys cancel each other out, resulting in a net force of 0, which makes your acceleration 0, right? So the velocity at which this occurs is called terminal velocity. Okay? So, but last year we never really sort of calculated drag force, all right? So this year, it turns out that because the shape of your object doesn't really change and the density of the fluid that your object is moving through doesn't change, we can usually express our drag force in one of two ways, all right? And these are how the problems are always set up on the AP test, all right? They'll say, suppose an object is moving and there's a drag force that is equal to some constant k times v, all right? So basically it's just saying that as your velocity gets bigger, so does your drag force, right? So sometimes they'll express the drag force like this, and then other times, for reasons that I have not yet been able to figure out exactly why they do this, sometimes they write it as kv squared, okay? So we need to know how to solve these two problems, all right? And they actually, they're challenging, which is why I always do this at the end of the year, because there's definitely some calculus knowledge that you're gonna need, okay? But so the problem is that as your velocity changes, your drag force changes. As your drag force changes, your net force changes. As your net force changes, your acceleration changes, right? And so everything becomes very, very complicated. All right. And so the question is, how do we deal with that? All right. And so that's what we're going to work on here. Okay. So let's dive in and do a problem. All right. So here's our first problem. So we've got here a box with a mass of 5 kilograms. It's on a frictionless horizontal surface and it's sliding along at 8 meters a second. Air resistance applies a force which is proportional to its velocity, and it can be expressed as FD, drag force, equals negative 4v squared. All right, and these are how the problems are always worded on the AP test. The first part of the question will say write, but do not solve a differential equation for the box's instantaneous speed v. All right, these are easy. Like you can totally just do this on autopilot. And some of you right now are like, well, what the bleep is a differential equation? All right, so I will explain that once we get to our answer and you'll see kind of what I mean. All right, so here's the process for this. All right, so for number one, I'm going to do everything for number one right here. Here are the steps we're going to follow. Step A, make a free body diagram. Step B, write a net force equals net force equation. Step C, all you're going to do is, so your net force, remember that's mass times acceleration. So you're just going to do one additional substitution, and this is the thing that's new. We're going to replace acceleration. We're going to write it as the definition of acceleration, right? Because our acceleration is changing. So the instantaneous acceleration is the derivative of velocity with respect to time. Okay, so those are our three steps. Free body diagram, net force equals net force, and then substitute dv dt instead of acceleration. Okay, so here we go. So let's do this. So here we've got a box of mass 5 kilograms sliding on a horizontal surface. So here's my horizontal surface, here's my box, 5 kilograms. It's sliding along with an initial velocity of 8 meters a second. Let's see what forces are on it. Well, gravity is going to pull it down. Normal force is going to hold it up. I don't really care about those because they're going to cancel out. And then we've got this drag force, right? Okay, so there's my free body diagram. So that's step A. Okay, step B. So this was step A. I don't know why I put that line there. Get rid of that. Okay, step B. Net force equals net force. So net force equals net force. So for us, that's mass times acceleration equals drag force, right? So that's step B, all right? I guess we could plug in our numbers here, right? We know our mass is 5 kilograms times A equals, and then our drag force is negative 4v squared, right? Okay, so that's step B. All right, and then step C, we're just going to substitute acceleration. So you get 5, A becomes dv dt equals negative 4v squared. there you go. That is the answer to number 1. Okay, that is our differential equation. All right, now what makes this a differential equation? Well, usually when we write a derivative, like suppose I give you this, the derivative with respect to x of 3x squared, we're taking our derivative with respect to x, and x is the variable in the problem, right? Here, we're taking our derivative with respect to t, but t is not the variable in it, okay? And so that's what makes this a differential equation, okay? All right, so that's always going to be the first part of the problem, is write but do not solve a differential equation that could be used to solve for the velocity v, and notice v is our variable there, okay? So that's the first part. Now, step 2 basically will now have you solve it, okay? So, step 2. Step 2. All right, so for step 2, it says write an expression for the box's velocity at time t. So in other words, we got to solve this mess, okay? Here's what you want to do. I haven't figured out a great way to word this yet, so I haven't written it out. I think the best way to do it is to do it just like see examples, okay? So the first thing we want to do is we want to separate our, so we'll do everything here in green. So number 2. So move dt to the other side. So I think that's going to be our first step. So this equation here, I'm just going to multiply both sides by dt. So that's going to give me 5 dv equals negative 4v squared dt. Okay. So then your next step is going to be move all v's to the dv side. And you're going to move, unfortunately, there are going to be problems where you can't move all of the constants, but you're going to move most constants. I'll explain this in a minute. To the dt side. Okay, so for us, what I'm going to do is I'm going to move my v's to the dv side. So I'm going to move this over here by dividing. Okay, and then this 5 is a constant. So I'm going to move the 5 over to the other side by dividing. Okay, so I'm going to divide everything by 5, and I'm going to divide everything by v squared. And so that gives me the following equation. I'm going to get dv over v squared, but on one side, and on the other side, I'm going to get negative 4 dt over 5. Okay? So there we go. So that's our first step, all right? Now, the next step is, so this statement on its own sort of doesn't really have any meaning. So to solve it, what we have to do now is we have to integrate, okay? So, oops, I wanted that to be a different color. Integrate. All right, so what I'm going to do is I'm going to integrate this from 0. So notice my variable of integration on this side is t. So I'm going to integrate from time 0 to time t. And on the other side, I'm integrating with respect to v. So I'm going to go from my initial velocity to my velocity at time t, which is what I'm looking for, right? So ultimately, what I'm going to do is I'm going to evaluate this whole mess, and this is the thing that I'm going to solve for, okay? So let's do the left-hand side of this thing, all right? So everything I'm going to do now is going to be this mess, okay? So, all right, so let's see. So the integral of dv over v squared. Well, we just learned how to do this, right? So this is the integral from vi. Well, we know our vi is 8, so I'm going to go ahead and put 8 there, v of t, and this is v to the negative 2 dv, right? Which is, well, let's see, I got to increase my power by 1. What do I have to multiply negative 1 by to get 1 is negative 1, okay, which is the same as negative 1 over v, right? But then I have to evaluate it at 8 and at v of t. So that gives me, remember, you always do final minus initial. So this is negative 1 over v of t minus negative 1 over 8, which is the same as So you're going to get 1/8 basically minus 1 over v of t, right? Okay, so that's the yellow side of this equation. All right, so now let's go back and do the other side of this equation, which actually is much easier. Okay, so now we're going to do this. Okay, so what I'm going to do here is I've got that constant there, -4/5. Let's pull that out. So this becomes, here we'll do, we'll do this in red, how about? So this becomes -4/5 times the integral from 0 to t of dt. Oh, well, the integral from 0 to t of dt is just t. So this is just -4/5 t. Haha! That one was not bad at all. All right? So now we can solve this, right? So here's our new equation. So now we've got this equals this. So I've got 1/8 minus 1 over v of t equals -4/5 t. Okay? So let's multiply both sides by -1 to get rid of this negative sign here. Okay? So if I do that, I get 1 over v of t minus 1 over 8 equals 4/5 t. So now I'm going to add 1/8 to both sides. So I get 1 over v of t equals 4/5 t plus 1/8. Take the reciprocal of both sides, and you get that v of t is 1 over this mess. And there's your answer. And on the AP test, I would say stop there. Okay. However, because I'm weird, I'm going to simplify this because I don't like that I have a fraction and a fraction. So I'm going to, on the bottom here, I'm going to find my least common denominator and add those two fractions. So you get this. The least common denominator is going to be 40, right? So you get 1 over 32t plus 5 all over 40, which then is 40 over 32t plus 5. So there's my expression. Velocity at time t is 40 over 32t plus 5. Okay? And notice, you can check, what is v of 0? If I put 0 in here, then I get 40 over 5, which is 8. Hooray! Okay? And also notice, as my time goes up, my velocity gets closer and closer to 0, but it never exactly reaches 0, does it? Okay? So, that is how you do those problems. All right? So the trick here, I guess the big thing that I should probably stress here is these bounds of integration that I used. So let me go back and highlight these. We'll do it in, I don't know, we haven't used orange yet. So notice my time goes from 0 to t, and my velocity always goes from the initial velocity to the velocity at time t. Okay, that'll always work that way. Okay? All right. So there's a next part to this. Part 3. How would it be different if our drag force had been -4v instead of -4v squared? All right, so let's see how that changes things. All right, so I'm going to basically go back and do the problem again, but with this new drag force, okay? So here we go. So number 1, right? Remember, so free body diagram, net force equals net force, and then do that substitution, A equals dv dt. Okay, so here we go. So for number 1, we're going to make our free body diagram. So here we go. You're going to have your gravity. You're going to have your normal force. You're going to have your drag force. Net force equals net force. Becomes mass times acceleration equals drag force. Substitute your numbers in. 5a equals, now my drag force is -4v, right? Instead of 4v squared. Okay. And then I'm going to substitute. This becomes 5 dv dt equals -4v. Okay, so that's my differential equation. Okay. Now, step 2. Now we got to solve this mess, right? So remember, to solve it, you always multiply both sides by dt. So I've got 5 dv equals -4v dt. Okay, and then you want to get all your constants on the dt side and all of your v's on the dv side. So I'm going to divide by 5, divide by v to give me dv over v equals negative 4/5 dt. All right? Okay, so now we got to integrate this thing. So my integral on the time side goes from 0 to t. Notice I kind of cheated there. I pulled the 4/5 out of the integral right away, didn't I? Okay, and over here, my integral goes from vi to v of t. Okay, so this side of my equation, well, let's see, dv over v, that's the one that uses the natural log, right? Remember, the integral of 1 over x dx, this is 1 over v dv, right? So this is just the natural log of v evaluated at vi, which is 8, right? And this is v of t, equals, on this side of the equation, well, this is the same as we had before. It's negative 4/5 t, right? Okay. So now I got to evaluate this thing. So this is going to give me the natural log of v of t minus the natural log of 8 equals negative 4/5 t. All right, and we got to solve this thing. All right, so here's where we're going to have to use our, so when I say solve this, we're trying to get v of t by itself. So here's where we're going to use our log principles. Okay, so the natural log of v of t minus the natural log of 8 is the same as the natural log of v of t over 8. And that equals negative 4/5 t. Okay, so now what we're going to do is we raise both sides of the equation to the, or you take e and raise it to that power. So e to that power, e to that power. All right, so here these guys cancel out. So I get v of t over 8 equals e to the negative 4/5 t. And now I can multiply both sides by 8. So I get v of t equals 8 e to the negative 4/5 t. Cool. And let's check. So there's our answer. And let's check what's v of 0. Well, if I put 0 in here, you get e to the 0, which is 1. And so e to the 0 is 1. 8 times 1 is 8. Hooray! So that worked also. Okay. All right, so one last example. So this last example is similar to the one we just did, but the natural log integral is a little bit trickier. I'm sorry I'm going long here. This is my second time doing this video. The first time I did it, it didn't work. My editing software does not work for some reason here on my personal computer. All right, so here we go. Oh shoot, I forgot to erase the screen. Ah. Whoa, what is going on? We'll just move that over there. Okay, sorry. Remember when I was saying I was going long and now I'm wasting a whole bunch of time erasing garbage? All right, sorry. Okay, so here we go. I don't know why that doesn't want to erase. Okay, so almost the same setup. This time though, our box is going to start at rest. So here we go. We got a box with a mass of 5 kilograms. So let's draw this. Here's our box, 5 kilograms. It's got an initial velocity of 0. Let's see. So we're going to have gravity and normal force that we're not going to care about because they're going to cancel out in this problem. Air resistance. Let's see. The box is pushed forwards with a force of 30 newtons. So let's assume that's a force from Roy. 30 newtons. Okay, and then the idea is as it speeds up, air resistance is going to push it back. So here is our drag force. So there's our free body diagram. Okay, so notice question 1 asks for the terminal velocity. Well, our terminal velocity occurs when our net force is 0, right? Because right now, Roy's force is bigger than our drag force, so it's going to speed up, speed up, speed up, until eventually the drag force will cancel Roy's force, right? So question 1, what's the fastest velocity the box will reach? That occurs when our net force is 0. That occurs when our drag force is, I guess, negative 30 newtons, right? So negative 4v equals 30, which means, oh, negative 30, sorry, which means the velocity is 7.5 meters per second just by dividing, right? So that's question A, that's our terminal velocity. okay, or question 1. That's our terminal velocity, okay? All right, now, so question 2, this is the thing. Write, but do not solve a differential equation for the box's instantaneous speed v, okay? So we've already got our free body diagram done. So let's get rid of all this stuff. All right, I'm so mad that I didn't erase this stuff. So here we go. So net force equals net force. So mass times acceleration equals force of Roy plus drag force or minus drag force, however you want to think about that. And so you get 5 dv dt equals 30 minus, what was our drag force? 4v. So there you go. So there's your differential equation. Okay. And then the final step of this, I got moved over here when I was doing my cutting and pasting. So this should be question number 3. Write an expression for the box's velocity at time t. So now we're going to solve this mess. Okay. So this is what we're trying to solve. So I'm going to bring that over and do a new page so I don't need to keep erasing. So here's what we've got. We've got 5 dv dt equals 30 minus 4v. Okay, so step 1, same as before. Multiply both sides by dt. So I'm going to get 5 dv equals 30 minus 4v dt. Okay, so now here was what I was saying before. Remember before I said you want to move most constants to the dt side? Here we can't move all of them. We can only move some of them. All right, because the only way I can move this v over to the other side is to divide by this whole mess. All right. So I'm going to get this. I'm going to get dv over 30 minus 4v, oops, 4v, sorry, equals dt over 5. Okay? All right, so now we're going to integrate this thing. So we're going to integrate from 0 to t, and we're going to integrate from our initial velocity, which was 0 this time, right, up to our velocity at time t. Okay? So here, this is, once again, we got to use a logarithm, right? So, because the 30 minus 4v is on the fraction and there's no exponent there, right? So this guy becomes the natural log of 30 minus 4v. But then if I take the derivative of that, I'm going to end up multiplying by the derivative of this, which is negative 4. So I think I have to divide by negative 4 so that when I take the derivative of this, it gives me this mess, right? Okay. And then I got to evaluate that at 0 and v of t. And then this side of the equation is just t over 5. Okay. So what are we going to do now? Let's see. Let's get rid of this minus 4. I'm going to multiply both sides by minus 4. So now I'm looking at the natural log of 30 minus 4v, evaluated at 0 and v of t, equals negative 4/5 t. And now I'm going to plug in my numbers. So I get the natural log of 30 minus 4 v of t minus the natural log of, let's see, if I plug 0 in, I'm just going to get 30, aren't I? Equals negative 4/5 t. Okay, so now we got to solve this. So once again, I've got the difference between two logs. So natural log minus natural log. So that gives me the natural log of 30 minus 4vt over 30 equals negative 4/5 t. Take e and raise them to the power, right? So we're going to go e to that power, e to that power. I think I might have been saying raise them to the e power instead of e to that power at the beginning of the video. So sorry if that was confusing. All right, so these guys cancel. So now I've got 30 minus 4v of t over 30 equals e to the negative 4/5 t. So we're trying to solve for v of t. So I'm going to multiply both sides by 30. So 30 minus 4v of t equals 30 e to the negative 4/5 t. And then algebra this thing, right? So this becomes 30 minus 30 e to the negative 4/5 t. Oops, I did that again. 4/5 t equals 4v of t. And then divide both sides by 4. And you get 7.5 minus 7.5 e to the negative 4/5 t equals v of t. Okay, and we can check. If you put 0 in for your time, then you end up getting 7/5 minus 7/5. And as t gets bigger and bigger, this guy gets closer and closer to 0, which is how you get that terminal velocity of 7.5 that we found at the beginning. Okay? I'm sorry this video went so long. I wish I had the power to edit, but I do not because my home computer is poopy. So now this is super intimidating to some of you. Remember, we're only given one problem per day. So try your first one, and then we'll troubleshoot the next time I see you. Okay? All right. Have a good one.